the clock that never existed. Imagine standing on a cold, silent mountain peak at midnight. The sky above is pitch black, devoid of a moon, devoid of clouds, yet ablaze with millions of motionless stars. Below you lies a world carved entirely from grey stone. The air is still. There is no breeze, no sound, no pulse in your chest, no rise and fall of your lungs. You wait. Minutes pass, hours pass, or perhaps centuries. How would you know? There is no sunrise. No shadow shifts across the ground. If nothing in the cosmos transforms, does the hour grow late? Or has the clock of reality vanished entirely? Now, look up at a single star directly above you. Without warning, it flickers. A pale shadow falls across the valley below. Something has shifted, and in that tiny, imperceptible moment, you feel a jolt in your mind, a whisper that tells you a brand new moment has just been born. For as long as humans have looked up at the night sky, we have carried an intuitive assumption that somewhere hidden in the fabric of nature, an invisible clock is ticking away. We tend to picture time as a vast, continuous river flowing quietly from an infinite past, rushing through the present and carrying everything forward into an unwritten future. We build our lives around this assumption. We measure it in seconds, organize it into years, and watch it etch lines into our faces. Yet, when we look across the history of physics, a startling possibility emerges. The flow of time may not be as straightforward as our everyday experience suggests. Is time a physical, fundamental pillar of the cosmos, a real stream carrying reality along? Or could the ticking clock we rely on every day be something far subtler, a framework created by our minds to make sense of a world in motion? To understand why science continues to wrestle with this question, we must travel back long before a single word was written on stone. A hunter steps outside his shelter long before dawn, his breath forming small clouds in the biting morning frost. He has no wristwatch. He does not know the word astronomy. He doesn't need to. He kneels and presses his hand against the frozen soil. A tiny shadow stretches across the ground, cast by the first beam of light cutting through the eastern mist. The stars are shifting. The long cold is beginning to yield. He knows it is time to move, not because he looked at a clock, but because the world around him changed. For hundreds of thousands of years, this was human existence. We did not measure time in abstract units. We tracked change. We watched the sun climb to its peak, felt the heat of noon, and saw our shadows lengthen as the day waned. We watched the moon grow bright, then wither into a dark crescent. Every natural cycle was a pulse. The Earth was not measuring time. It was turning on its axis, carrying us through light and shadow. Then, human civilization sought precision. Ancient cultures built tall obelisks that cast long, steady shadows across stone plazas. They crafted water vessels that dripped drop by drop through tiny copper holes. Centuries later, in quiet European monasteries, blacksmiths forged iron gears and swinging pendulums, creating the first ticking mechanical clocks. We were no longer merely following the slow breath of the sun. We were marching to the artificial rhythm of iron teeth clicking against iron teeth. By the mid-20th century, we pushed our obsession further. We built atomic clocks that measure the ultra-fast vibrations of cesium atoms, counting billions of microscopic oscillations every second. Today, these atomic ticks sync global communications, guide high-speed financial networks, and pinpoint satellites floating in orbit. We spent thousands of years refining the clock, assuming we were building finer, sharper tools to measure the invisible river of time. Yet, a simple, haunting question remains. Look closely at the most precise atomic clock ever built. Look past its laser tubes and digital displays, down into the heart of the machine. What is it actually measuring? It is watching an atom vibrate back and forth. That is all. The pendulum does not touch time. It swings through space. The gear does not turn through time. It rotates on an axle. The cesium atom does not count seconds. It shifts between energy states. Every clock we have ever built is simply a contained piece of the universe moving in a predictable pattern. We use one motion to measure another motion, which brings us face to face with a fundamental puzzle. Do our clocks measure an independent physical dimension called time? Or do they simply track physical change? Imagine a sealed room drifting deep in the void between galaxies. Inside this room sits a single glowing candle. Its flame flickers, casting soft light against the walls. The wax slowly melts, dripping down the stem and pooling at the base. You watch the wax melt and say, "Time is passing." Now, imagine we freeze the physical system. The flame stops in mid-flicker. The falling drop of wax stops in mid-air. Every atom, every photon, every electron comes to an absolute standstill. Does time keep flowing through that frozen room? For centuries, Sir Isaac Newton argued that it did. He proposed that even if every particle in the cosmos stood perfectly still, an absolute universal time would continue its steady, relentless march forward. It is an intuitive picture. It gives us an absolute background, a cosmic stage upon which reality plays out. Yet, when theoretical physicists look closely at the equations of nature, that background becomes far harder to find. Without change, how do we define a before or an after? Is time an independent stage upon which events occur, or is time born entirely from the interactions of matter and energy? Consider how your mind experiences this moment right now. Your eyes receive photons that bounced off a surface a few nanoseconds ago. Your ears process sound waves generated moments earlier. Your brain takes these incoming signals, organizes them alongside your memories, and constructs a continuous experience you call the present. You remember yesterday. You anticipate tomorrow. Because your biology is structured this way, you feel as though you are moving through a stream, swept from a fixed past toward an unwritten future. Yet across the landscape of modern physics, that simple stream turns out to be one of the deepest, most contested mysteries in science. When we examine the fundamental laws of nature, we find that many equations operate with surprising symmetry, working just as smoothly backward as they do forward. Why then does our macroscopic world move strictly in one direction? Why do cups shatter but never unshatter? Why do we remember the past but never the future? Is the flow of time an objective law built into the fabric of the universe? Or is it an emergent feature of entropy, statistics, and human perception? Science has spent centuries attempting to answer these questions, and the journey has taken us far beyond anything our ancestors could have imagined. Over the chapters ahead, we will see how Albert Einstein shattered the idea of a universal clock, showing that time can stretch, slow, and warp. We will journey to black holes, where the flow of time fractures. We will enter the subatomic quantum realm, where cause and effect lose their macroscopic certainty. And we will look to cosmology to ask whether time had a beginning, and whether it will have an end. We build clocks to bring order to our lives, but in trying to measure time, we stumbled upon the greatest puzzle in physics. Every clock we have ever built measures change. So what exactly is time? The journey to find out begins now. Does anything actually move through time? Take a slow, deep breath and allow the quiet around you to soften the edges of the day. Imagine standing on a silent, sunlit plain. Above you, A single hawk hangs suspended in midair, its wings spread wide against a pale blue sky. A single drop of rain is frozen, a few inches above a blade of grass. A falling leaf hovers halfway to the ground. Nothing is falling. Nothing is rising. Nothing is breathing. In this frozen frame, you step forward. You walk past the suspended raindrop, beneath the motionless bird, and across the silent meadow. You feel yourself taking steps. You feel your heart beating in your chest, and a quiet, perplexing question begins to form in your mind. If the world around you has stopped changing entirely, are you still moving through an invisible current called time? Or are you simply changing the arrangement of your body within a completely stationary physical landscape? In our daily human experience, we naturally assume that time has a built-in direction. We watch smoke rise from a dying campfire or a ripple spread across a still lake, and we feel as though we are witnessing the relentless forward march of reality. We imagine that the past is a realm that has been destroyed, and the future is a realm that does not yet exist. We believe that we, and every star in the heavens, are constantly being carried forward through an invisible temporal medium. Yet, when we look at the mathematical framework that describes our physical world, a startling contradiction emerges. Consider a simple, elegant interaction. Imagine watching a high-speed camera recording of a glass sphere rolling across a smooth surface. It collides with a second sphere, transferring its kinetic energy, and sends the second sphere gliding smoothly away into the darkness. Now, imagine playing that video in reverse. The second sphere glides backward out of the dark, strikes the first, and sends it rolling smoothly back to its starting point. If you showed both clips to a physicist without revealing which was recorded first, they would tell you something remarkable. Many of the fundamental equations that describe classical mechanics, electromagnetism, and quantum wave dynamics work with equal validity in either direction. The core laws of motion do not contain a built-in preference for forward or backward. They simply describe mathematical relationships between physical states. To the basic interactions of nature, the concept of a direction in time is surprisingly elusive. This brings us to a deep physical dilemma. If several of physics' most fundamental equations do not mandate a one-way flow of time, why does our world feel so rigidly one-directional? Why do physical systems seem to evolve in a single, predictable sequence? To understand this, we must examine what actually occurs when something moves. Think of a clock hanging on a wall. As its second hand ticks, we say that time is passing. But if you look closely at the mechanism itself, all you are observing is spatial displacement. A hand is moving through an angular distance. Gears are rotating around axles. Electrical currents are flowing through wires. When an object moves across a room, or when a planet orbits a star, nothing is physically traveling through an invisible dimension of time. Matter and energy are simply altering their spatial relationships to one another. When we observe what we call motion, we are not witnessing objects traveling along an invisible river of time. We are witnessing physical systems transitioning from one geometric configuration to another. The components of these systems, the fundamental particles that construct our reality, do not bear the marks of age. An electron bound within a molecule today exhibits the exact same intrinsic properties as an electron that existed billions of years ago. The elementary building blocks of nature do not decay, rust, or grow old in the way macroscopic objects seem to. They simply interact, shift positions, and form new patterns. When theoretical physicists reflect on this realization, it challenges our deepest assumptions about existence itself. We naturally perceive ourselves as passengers riding a moving temporal wave. But physical law suggests a far more subtle possibility, that motion is purely spatial, and that the universe does not flow from one second to the next. Instead, the cosmos may simply exist as a vast, interconnected landscape of configurations. What we experience as the passage of hours may not be the movement of the universe through time, but rather the internal shifting of physical states within a reality that remains, at its deepest level, fundamentally anchored in space. We do not need to picture ourselves as fragile objects being swept away by an unstoppable temporal current. We are structured patterns of matter and energy, participating in an ongoing, elegant physical transformation. As the night settles around you and the quiet grows deeper, let your mind rest in this vast perspective. The pressure to keep pace with an invisible, rushing clock begins to fade, leaving behind a profound sense of stillness. Entropy, the engine of time. Allow your breathing to slow down completely. Let the room around you fade into a gentle, dark stillness as we enter one of the most remarkable chapters in the history of science. Imagine holding a small, solid sphere of clear blue ice in the palm of your hand. It is smooth, cold, and beautifully structured. Beneath its surface, billions upon billions of water molecules are locked into a precise, crystalline lattice, a silent, intricate geometry frozen in space. Now, close your eyes and hold it in the quiet warmth of your hand. You feel the sharp cold slowly yield, the hard edges soften. A tiny trickle of water slides past your fingers. Within minutes, the solid crystal has completely transformed into a small pool of liquid resting in your palm. Now, imagine standing in that quiet room for 1,000 years. No matter how long you wait, no matter how cold the surrounding air becomes, that pool of water will never, on its own, gather its scattered molecules, reassemble its crystalline lattice, and leap back into a solid sphere of ice in your hand. Why? If the fundamental equations of motion work equally well in reverse, why does nature only move in one direction? Why does ice melt, but never unmelt? Why do stars burn out, but never spontaneously gather their scattered light and reignite? The answer to this mystery is not found in an invisible clock ticking in the sky. It is driven by a single, inescapable principle that governs every corner of the cosmos, a concept known as entropy. To understand entropy, we must step away from abstract mathematics and look at the sheer probability of how our universe is built. Picture a simple box divided down the middle by an invisible line. On the left side of the box, we place 50 microscopic gas molecules trapped in a tight, orderly cluster. The right side of the box is completely empty. This arrangement, where every single molecule is neatly confined to one side, is a state of extraordinary order. Now, imagine removing the barrier. The molecules begin to move, bouncing off the walls and colliding with one another in random directions. Within a fraction of a second, they spread out, filling the entire box evenly. If you ask a physicist how many ways there are for those molecules to stay neatly packed on the left side of the box, the answer is very few. But if you ask how many ways there are for those molecules to be scattered randomly throughout the entire box, the answer is trillions upon trillions. The gas does not spread out because a physical force is pushing it. It spreads out simply because a state of disorder is infinitely more probable than a state of order. This is the true nature of entropy. It is not a mysterious force. It is simply the measure of how scattered, disorganized, and dispersed a system's energy has become. The universe does not move forward because time is flowing. The universe evolves because it is constantly moving from rare, highly organized states into vastly more common, disorganized states. Entropy is not the clock. Entropy is the engine. This simple realization solves one of the greatest puzzles in physics. It creates what scientists call the arrow of time. Think of a freshly brewed cup of coffee left sitting on a wooden desk. Its heat is tightly concentrated within the liquid, a state of high organization. As the minutes pass, that heat naturally bleeds out into the cooler air of the room, spreading until the cup and the room reach the exact same temperature. The heat never spontaneously gathers itself from the air and concentrates back into the liquid to make the coffee hot again. The energy has dispersed into a state of higher entropy. Every single event you witness in the physical world, from a mountain slowly eroding under the rain to a distant star radiating its warmth into the cold void of space, is a story of energy spreading out. Without entropy, the universe would be a static, unchanging movie frame. There would be no chemical reactions, no falling rain, no burning suns, and no thoughts forming in a human brain. We do not experience time because an invisible river is carrying us into tomorrow. We experience time because our universe began in a state of stunning, exquisite order, and has been slowly, gracefully unpacking that order ever since. Yet, when theoretical physicists trace this chain of cause and effect back to its ultimate source, they arrive at a question so profound that it borders on terror. If entropy is constantly increasing, if disorder is always growing, where did all the original order come from? If you follow the arrow of time backward, past the birth of cities, past the formation of Earth, past the birth of the very first stars, you eventually reach the earliest accessible moment in cosmic history, the Big Bang. Physics reveals that at the very beginning of our cosmos, nearly 14 billion years ago, all the matter and energy in existence was compressed into a state of unimaginable density, uniformity, and microscopic order. It was a state of extraordinarily low entropy. Why the universe began in such a hyper-ordered condition is one of the greatest unsolved mysteries in modern science. It is a cosmological puzzle that keeps astrophysicists searching for answers at the very limits of knowledge. If the cosmos had been born in a state of maximum disorder, no stars would have ever condensed, no planets would have formed, no quiet nights would exist for anyone to look up at the dark sky. Every breath you take, every starlight photon that reaches your eyes, and every beat of your heart is powered by the lingering energy of that pristine, highly ordered beginning. Now, as the stillness of the night wraps around you, let the weight of this cosmic journey bring a deep, soothing quiet to your mind. The sense of time passing is not something to be feared or chased. It is simply the gentle, majestic unfolding of the universe's original order. A quiet balancing of energy across the vast expanse of space. You are not watching time slip away. You are witnessing the cosmos slowly, peacefully spreading its heat, sharing its energy, and resting into an eternal, quiet balance. Einstein destroyed absolute time. Close your eyes and let the darkness behind your eyelids expand into a deep, silent void. Imagine two identical twin sisters standing together on a launched pad in the quiet of a desert night. They are the exact same age, down to the very microsecond. Their hearts beat at the same slow, resting rhythm. Their cells age at the exact same biological pace. One sister steps onto a spacecraft. The engines ignite without a sound in the vacuum of space, accelerating her craft away from Earth until she is traveling through the dark at 99% the speed of light. The other sister remains behind, standing silently in the desert, watching the faint red trail of the engines vanish into the stars. Decades pass on Earth. The sister on the ground grows old. Her hair turns silver. Her skin softens with time. She watches decades of seasons turn, winter into spring, 50 times over. Then, the spacecraft returns. The heavy airlock doors unseal with a slow hiss. the traveling sister steps out onto the desert sand. She has not aged 50 years. To her body, her heart, and her wristwatch, only 7 years have passed. She looks upon her twin sister, once her identical peer, and finds an elderly woman standing before her. This is not a theoretical fantasy. It is not a glitch in human biology, nor a failure of mechanical clocks. It is the raw, undeniable geometry of our universe. And it shatters the single most comforting assumption humanity ever held about reality. For centuries, Sir Isaac Newton gave us a world that made sense. He envisioned an absolute, universal time, an invisible cosmic clock hanging over the universe, ticking at the exact same unyielding rhythm for a person on Earth, an astronaut near Mars, and the star burning at the edge of the galaxy. In Newton's universe, a second was a second, everywhere and forever. It felt safe. It felt logical. Then, in 1905, Albert Einstein looked at a single, radical experimental reality that no one could explain. No matter how fast you move toward or away from a beam of light, its speed through empty space never changes. It is always roughly 300,000 kilometers per second. To keep the speed of light perfectly constant for every observer in the cosmos, nature must make a terrifying sacrifice. It sacrifices the uniformity of time itself. If you travel at high speeds through space, time inside your reference frame does not merely feel different. It fundamentally runs slower relative to someone standing still. Every chemical reaction in your blood slows down. Every electrical impulse firing between the neurons in your brain takes longer to travel. The ticking of your watch, the vibration of your atoms, the decaying of your cells, everything slows down in perfect, seamless synchronization. You do not feel sluggish. To you, 1 second feels completely normal. But relative to the stationary world you left behind, you are drifting through reality at a different temporal pace. If this sounds impossible to believe, consider a tiny particle created at the very edge of our atmosphere. The muon. Muons are unstable subatomic particles born when cosmic rays strike the upper atmosphere, 20 kilometers above the Earth. A muon lives for a fraction of a blink, just 2 microseconds, before it spontaneously disintegrates. Even if a muon traveled toward Earth at nearly the speed of light, 2 microseconds is only enough time for it to cover about 600 meters. Mathematically, not a single muon should ever reach the ground. Yet, every single second, thousands of muons strike the palm of your hand. How? Because to the muon, traveling through our atmosphere at nearly the speed of light, time itself slows down. Its 2 microsecond lifespan stretches. From our perspective on Earth, the particle's internal clock ticks so slowly that it survives the long journey through 20 kilometers of atmosphere and reaches the surface. We do not have to guess if Einstein was right. We catch the evidence in our hands every moment of the day. In 1971, physicists took 4 hyper-precise atomic clocks, placed them aboard commercial airliners, and flew them completely around the world. When they landed and compared them to identical atomic clocks that remained stationary on the ground, the difference was unmistakable. The flying clocks were younger. Time had physically ticked slower for the travelers on the plane. The destruction of absolute time forces us to confront a consequence so unsettling that it fundamentally alters what it means to exist in the present. There is no universal now. Right now, as you listen to these words, you assume there is a single cosmic present moment happening across the entire universe, that whatever is occurring on Earth right now corresponds to a matching right now on a distant galaxy billions of light years away. Einstein proved this is an illusion. Because time passes at different rates depending on how you move through space, Two observers moving relative to each other will never agree on whether two events happened at the same time. What is the future for one observer can be the present for another, and the past for a third. There is no master clock in the heavens. There is no central timestamp for the universe. The universe is not a single story unfolding step by step on a single stage. It is an infinite tapestry of personal times, each weaving its own thread through the fabric of space. As the night settles around you and the quiet grows deeper, let the sheer wonder of this universe hold your mind in awe. You are not locked into a rigid mechanical clock ticking away your life in a cold universe. You exist within a flexible, stunning four-dimensional reality. A universe where space and time bend gracefully around speed, matter, and light. The seconds of your life are uniquely yours, measured by your own path through the cosmos, woven into a reality far stranger and more beautiful than we ever imagined. In our next chapter, we will discover how an even greater force warps this fabric, exploring how the heavy mass of planets, stars, and black holes can slow time down to a crawl, creating places in the cosmos where a single hour lasts longer than a human lifetime. Gravity slows time. An astronaut hovers in a small spacecraft just outside the gravitational shadow of a supermassive black hole. Through the thick, reinforced viewport, she looks down at a terrifying abyss. A sphere of absolute, light-swallowing blackness, encircled by a blinding ring of white-hot gas, spinning at near the speed of light. She checks her instrument panel. The navigation clock ticks steadily. 1 second. 2 seconds, 3 seconds. Her heart beats at a normal, resting pace of 60 beats per minute. She sips warm water from a pouch. Everything inside the cabin feels completely ordinary. She remains in this position for precisely 60 minutes. Satisfied, she turns her ship around, fires her thrusters, and escapes the black hole's gravitational pull to return to Earth. She expects to be greeted by her ground control team. She expects to see the familiar blue marble of her home planet, unchanged, waiting for her arrival. Instead, when her ship drops into Earth's orbit, she gazes down at a silent, unfamiliar world. The continents have subtly drifted. The ice caps have melted into unrecognizable coastlines. The night side of the planet, once glowing with sprawling, vibrant webs of human cities, is utterly, completely dark. She tries to contact ground control. Only cosmic static answers. She aged exactly 1 hour. On Earth, 500 years have vanished into dust. Dynasties rose and collapsed. Languages evolved and died. Everyone she ever knew, loved, or spoke to died centuries ago. Their bones long turned to ash, while she drank a single pouch of water in the quiet shadow of a cosmic monster. She did not travel through time using a science fiction machine. She did not jump through a wormhole. She simply stood in a place where gravity was strong enough to crush the rhythm of reality itself. How is this possible? How can 60 minutes in one corner of the universe equal 5 centuries in another? To understand this mind-bending reality, we must confront a truth so fundamental that it shatters our everyday intuition. Gravity slows down time. Not metaphorically. Literally. For centuries, we were taught that gravity was merely an invisible rope pulling objects toward the ground. An apple falling from a branch, or the moon swinging around the Earth. Albert Einstein realized something far stranger. He proved that mass, whether it is a boulder, a planet, a star, or a black hole, physically warps and bends the four-dimensional fabric of space-time around it. And when you curve space, you inevitably curve time. Where gravity is weak, in the empty voids between galaxies, the temporal landscape is smooth and vast. Clocks tick fast. Where gravity is strong, deep inside the heavy gravitational wells created by massive objects, Space-time is tightly compressed. Clocks run slow. You do not need to travel to a black hole to experience this warping. It is acting upon your body at this exact second. Your feet sit closer to the center of the Earth than your head. Because your feet are positioned deeper inside Earth's gravitational well, gravity pulls on them slightly harder. As a direct consequence of physics, your feet are living in a slightly slower temporal stream than your brain. Over a human lifetime of 80 years, the top of your head will age roughly 90 nanoseconds faster than the soles of your feet. It is a microscopic difference, imperceptible to human senses. But it is physically real. In fact, the modern digital infrastructure that connects our civilization would instantly collapse if we ignored this terrifying law of nature. 20,000 kilometers above your head, a constellation of GPS satellites orbits the Earth. Up there, high above the planet's surface, the Earth's gravitational pull is significantly weaker. Because of this weaker gravity, general relativity dictates that the atomic clocks on those satellites run faster than clocks on the ground by roughly 45 microseconds every single day. Even when accounting for their orbital speed slowing them down by 7 microseconds, their net clocks still gain 38 microseconds every 24 hours. 38 microseconds sounds insignificant, but light travels 300 meters in a single microsecond. If satellite engineers failed to reprogram those atomic clocks to account for Einstein's gravitational equations, your smartphone's map would be inaccurate within minutes. Within a single day, GPS location tracking on Earth would drift by over 10 kilometers. Airlines would be grounded. Autonomous ships would run aground. Financial markets synchronized by satellite timestamps would crash. Our globalized world functions only because we adjust our technology to account for the fact that time moves at different speeds at different altitudes. Now, push this principle to its absolute extreme. If Earth's modest mass can shift time by microseconds, what happens when you crush the mass of 3 million suns into a region so dense that physics predicts a singularity, near the boundary of a black hole? The event horizon. If an observer watched you fall toward the event horizon from a safe distance through a powerful telescope, they would never actually see you cross the boundary. To their eyes, as you sank deeper into the intense gravitational well, your clock would slow down to a crawl. The light reflected off your ship would stretch into long, faint infrared waves. They would watch your ship freeze at the edge of the abyss, suspended in a permanent, silent snapshot for eternity. To the outside universe, you never enter. To you, you fall straight through in a matter of seconds. Two observers looking at the exact same moment, experiencing two completely different realities. Look up at the night sky. The universe is not a uniform arena where a single clock ticks away the hours for everyone equally. It is a vast, heavy, dynamic landscape filled with deep valleys and steep mountains of time. Time slows to a crawl near the colossal hearts of galaxies, races across the empty voids of deep space, and bends around every planet, moon, and star. The rate at which your life unfolds is intimately tied to where you stand in this cosmic terrain. In our next chapter, we will push past this threshold of no return, venturing inside the dark event horizon itself to discover what happens when gravity becomes absolute, and time and space swap places entirely. Inside a black hole. Imagine dropping a smooth glass marble off the side of a tall bridge on a windless night. You let go. For the first few seconds, you can reach out, close your hand, and catch it. The choice to reverse its journey remains yours. As it accelerates into the dark, that window of choice shrinks. It falls faster and faster, passing the point of no return, until it strikes the black water below with a faint splash. The marble is gone. The splash settles. The water turns flat again. Now, imagine that the bridge is not spanning a river, but the fabric of space-time itself, and the water below is an event horizon, the outer boundary of a black hole. From the outside, a black hole looks like a sphere of absolute, light-swallowing darkness, wrapped in a blinding, twisted disk of incandescent gas. It looks like an object, a dark star floating in the quiet void. But a black hole is not an object. It is a place where the geometry of reality has fractured. It is a region of space where gravity has overwhelmed every other fundamental force in nature, curving space-time so violently that space and time literally trade places. And if you cross that invisible boundary, you discover a truth far more terrifying than death. The future ceases to be a point in time. The future becomes a physical location in space. To understand what happens when you plunge into this cosmic trap, we must follow an astronaut who has made the final, irreversible decision to cross the threshold. She steers her capsule away from her mothership, floating at a safe distance in deep space. Her thrusters fire with a muted rumble, sending her gliding silently toward the black sphere ahead. As she approaches, the light from the universe behind her begins to warp. The stars do not look like points of light anymore. They are dragged and smeared into brilliant, glowing arcs that wrap around the darkness like a halo. Her instruments track her descent. She approaches the event horizon, the point where the escape velocity of gravity equals the speed of light. If she fires her engines at maximum thrust now, she can still turn back. Her ship consumes fuel, breaks free from the gravitational pull, and climbs back into the safety of the open cosmos. She hesitates for a single heartbeat. Then, she cuts the engines. She drifts forward. There is no physical wall at the event horizon. No alarm sounds inside the cabin. No dramatic explosion marks the boundary. Passing through the horizon is as quiet and imperceptible as stepping across the shadow of a cloud on a summer afternoon. To her own senses and her own body, nothing instantly breaks. Her watch continues to tick. Her pulse remains steady. But the universe she left behind has just vanished forever. The moment she crosses the horizon, a mind-bending inversion occurs within the mathematical fabric of space-time. Outside the black hole, in the ordinary universe, you have complete freedom to move in any direction through space. You can walk forward, step backward, climb upward, or sit completely still. Yet, you have zero freedom in time. You are forced, second by second, to move into the future. You cannot pause the clock, and you cannot walk backward into yesterday. Inside the event horizon, gravity turns this geometry upside down. The radial direction, the path leading directly toward the center of the black hole, swaps its mathematical role with time. Moving deeper toward the center is no longer a spatial choice. It becomes a temporal direction. The singularity at the heart of the black hole is no longer a point in space sitting ahead of her ship. It is an inevitability in time. Trying to escape a black hole once you are inside is not like trying to fly out of a deep canyon. It is like trying to turn your spacecraft around and fly into yesterday. Even if her engines possessed infinite energy, steering her ship away from the center would be as impossible as trying to stop yourself from turning 1 minute older. Every direction her thrusters point leads inevitably toward the center, because every path into the future points downward. As she falls deeper into this temporal trap, the extreme curvature of space-time begins to exert an agonizing physical pull on her ship. This is the relentless process known to astrophysicists as spaghettification. Because gravity grows exponentially stronger with every millimeter she falls, the gravitational pull on the feet of her spacecraft is significantly higher than the pull on the nose. The front of her ship is accelerated downward faster than the back. At the same time, The space-time grid itself is compressed laterally, squeezing the sides of her capsule inward while stretching it vertically. Space itself is behaving like a relentless vice, stretching matter into an infinitely thin, thread-like strand as it plunges toward the center. And what does she see if she looks out the rear viewport, back toward the universe she left behind? She sees the entire future history of the cosmos compressed into a shrinking circle of brilliant light above her head. Because time outside the black hole is racing at near infinite speed relative to her internal clock, she watches galaxies collide, stars burn out, and centuries flash past in fractions of a second. She is witnessing the end of the universe play out in a blinding, condensed finale right before her eyes. And then, she reaches the end of the journey. Here, the smooth, four-dimensional fabric of space-time is torn open entirely. The equations that have guided our understanding of gravity, motion, and light break down and yield nonsense. Infinities spill across the chalkboard. Physics, as we know it, simply stops speaking. Most modern theoretical physicists believe that a literal, physical infinity does not exist in nature. Instead, the breakdown of Einstein's equations of the center of a black hole is a loud, screaming signal that our current understanding of reality is incomplete. At this microscopic, ultra-dense scale, gravity must merge with the bizarre, probabilistic world of quantum mechanics, a realm where space and time may no longer be smooth dimensions at all, but a chaotic, flickering foam of quantum probabilities. The singularity is not an end to the universe. It is the frontier where our current human knowledge reaches its absolute edge. As you rest in the deep, undisturbed quiet of your room, gaze into the vastness of this realization. The universe contains places so extreme that the familiar rules of our daily existence, before and after, near and far, past and future, dissolve entirely into pure geometry. Black holes are not mere destroyers of matter. They are cosmic monuments to the flexibility of space-time, reminders that the reality we inhabit is far stranger, darker, and more magnificent than our senses could ever perceive. In our next chapter, we will step out of these gravitational abysses and examine a paradox that strikes at the core of human existence, asking whether the past, the present, and the future all exist simultaneously in an eternal, unchanging block of reality. The block universe. Imagine holding a finished hardbound book in your hands. You run your thumb across its edge, fanning through 300 pages of crisp paper. Chapter 1 sits bound near the beginning, depicting a cold morning decades ago. Chapter 15 lies near the middle, describing a quiet afternoon in the sun. The final page sits permanently bound at the end, holding the story's quiet conclusion. If you open the book to page 90, the characters on that page are alive, speaking, and experiencing their present moment. To them, page 89 feels like a vanished memory. Page 91 feels like an unwritten future waiting to be born. But holding the volume from the outside, an observer sees a stunning reality. Page 1, page 90, and page 300 exist simultaneously within the physical structure of the book. Page 1 has not dissolved into non-existence, and page 300 is not waiting to be created. Now, look up from the book and look around your room. What if our four-dimensional universe is built upon a similar geometry? What if the moment you took your very first breath as a child, the moment you are listening to these words right now, and the moment a distant descendant looks up at the night sky centuries from now, are all permanently embedded in a vast four-dimensional structure that simply is? For many physicists and philosophers, Albert Einstein's theory of relativity naturally points toward this breathtaking, mind-bending interpretation of reality, a model known as the block universe. To understand why relativity pushes our thinking toward this model, we must re-examine one of Einstein's most radical insights: the relativity of simultaneity. Imagine a man sitting on a park bench on Earth, watching dry autumn leaves float down from an oak tree. At the exact same instant, by his local clock, an alien sits inside a research vessel on a planet billions of light years away. If the alien remains completely stationary relative to Earth, their present moments align. The alien's now matches the man's, now on the park bench. Now, imagine the alien gets up and walks slowly away from Earth at just 3 miles an hour. Because high speed or vast distance relative motion tilts the plane of simultaneous events across space-time. That tiny walking pace across billions of light years rotates the alien slice of the present. Across cosmic distances, that microscopic tilt sweeps through centuries of Earth's history. Suddenly, the alien's present moment no longer aligns with the man on the park bench. The alien's now aligns with Earth in the 19th century, a world where steam locomotives are new, and the man on the park bench won't be born for generations. If the alien turns around and walks slowly toward Earth, the plane of simultaneity tilts in the opposite direction. Now, the alien's now sweeps forward into Earth's distant future, aligning with a world where our cities may be silent ruins and the park bench has long decayed into dust. This thought experiment does not mean the alien can physically see our future or alter our past. However, it poses a profound question that keeps theoretical physicists up late into the night. If an observer's motion through space determines whether your past or your future is their present, then can we truly say the past has vanished, or that the future does not yet exist? This radical framework is known as eternalism. In our daily lives, we naturally operate under a different perspective called presentism. We intuitively believe that only the razor-thin slice of time called now possesses physical reality. We treat the past as a ghostly memory that no longer exists, and the future as a void waiting to be constructed. This thought experiment does not mean the alien can physically see our future or alter our past. However, it poses a profound question that keeps theoretical physicists up late into the night. If an observer's motion through space determines whether your past or your future is their present, then can we truly say the past has vanished, or that the future does not yet exist? This radical framework is known as eternalism. In our daily lives, we naturally operate under a different perspective called presentism. We intuitively believe that only the razor-thin slice of time called now possesses physical reality. We treat the past as a ghostly memory that no longer exists, and the future as a void waiting to be constructed. Eternalism proposes the exact opposite. In the four-dimensional space-time block, a structure physicists describe as a static continuum, time does not flow. There is no physical river carrying reality from yesterday into tomorrow. There is no glowing wave of now physically sweeping across the cosmos. Instead, space-time is envisioned as a four-dimensional tapestry containing every coordinate of space and time. Your life in this model is not a fleeting spark that flashes for a fraction of a second and disappears into the dark. Your life is a continuous four-dimensional path carved into space-time. A world line. Page 1 of your story, page 90, and page 300 are all static features of this cosmic architecture. If an observer could stand outside our four-dimensional universe and view the space-time block from the outside, they would not see events unfolding step by step. They would see your entire existence laid out like a luminous thread woven into the fabric of space. Your childhood, your adulthood, and your quietest moments, all coexisting as permanent coordinates in the geometry of reality. Yet, this picture raises an agonizing question that physics itself has not settled. If the future exists as a coordinate in the space-time block, what becomes of human choice? Is our destiny rigidly predetermined, or is the block universe merely an incomplete picture of a far stranger reality? Physicists and philosophers remain deeply divided. Some argue that determinism is absolute, that the future is as unchangeable as the past, and our feeling of making real-time choices is simply a biological illusion created by our brain's forward-marching memory. Others suggest that quantum mechanics shatters this static block, that at the microscopic level, reality remains probabilistic, continually branching into infinite possible futures. And still others hold to the growing block universe theory, where the past and present are frozen into space-time, but the future remains an open, unwritten horizon. Physics does not yet give us a final answer. The block universe remains an interpretation, one of the most compelling and mathematically elegant ways of visualizing Einstein's equations, but still a frontier where quantum mechanics and relativity struggle for dominance. What it undeniably offers us, however, is a radical shift in how we view existence itself. In this four-dimensional view, death is not an erasure. It is simply a spatial boundary, the edge of a world line in a specific region of space-time, just as a mountain has a physical boundary where its peak meets the sky. The moments of your life do not disappear into a phantom realm. They remain written onto their specific pages of the cosmic volume. As you lie in the quiet dark of your room, let this awe-inspiring uncertainty rest gently in your mind. We inhabit a universe whose ultimate structure remains gloriously, tantalizingly unknown. Whether time is a rushing river, a branching tree, or an eternal frozen block of four-dimensional space, one truth shines clearly through the equations of modern science. Reality is far richer, far stranger, and far deeper than our senses were ever built to perceive. In our next chapter, we will step directly into the quantum realm, discovering how subatomic particles challenge the very nature of cause and effect, and asking whether the future might actively reach back to shape the past. Does the future already exist? Imagine setting up a line of 1,000,000 black dominoes across an endless wooden floor. Each domino is placed at an exact distance from the next. You carefully inspect the line, calculating the height of every piece, the mass of the wood, the angle of the floor, and the faint draft in the air. You raise your index finger and gently press the very first domino. It tips forward. It strikes the second piece with a sharp, clean click. The second strikes the third, sending a cascading wave of falling wood racing across the floor into the darkness. Before the wave reaches the 10,000th domino, you step away, sit down in a chair, and ask yourself a simple question. Is the fate of the final domino already sealed? Do the mass of the pieces, the speed of the fall, and the unbroken chain of cause and effect mean that the last domino was doomed to fall the exact microsecond your finger touched the first? Or could something at the microscopic foundation of nature break the sequence and leave that final domino standing? This simple thought experiment sits at the heart of one of the deepest, most fiercely contested questions in all of science. Is the future a rigid, inescapable trajectory already written into the fabric of reality? Or is it an unwritten ocean of pure probability? For centuries, classical physics gave us a clockwork universe that left no room for uncertainty. In the late 18th century, the French mathematician Pierre-Simon Laplace proposed a thought experiment that would define scientific thinking for generations. Laplace argued that if a hypothetical supreme intellect, what we now call Laplace's demon, could know the exact position and velocity of every single atom in the cosmos at one specific moment, it could use Isaac Newton's laws of motion to calculate the entire history of the universe with absolute mathematical certainty. To such an intellect, nothing would be uncertain. The birth of Earth, the formation of every star, every choice you make, and the final breath of the cosmos would be pre-calculated down to the last decimal place. In this classical deterministic view, the feeling that you are choosing your own path is merely a biological illusion. You feel as though you are deciding what to think or where to walk next. But in reality, every neuron firing across your brain is simply a physical particle responding to the laws of chemistry and electromagnetism. A domino falling because the domino before it tipped over. Under classical mechanics, the future isn't just predictable in theory. It is as fixed, immobile, and unalterable as the past. Yet, as the 20th century dawned, physics stumbled upon a subatomic realm that shattered Laplace's clockwork machine. The realm of quantum mechanics. Consider a simple, real-world experiment that you can build in a physics laboratory today. Place a single radioactive atom, such as radium, beside a particle detector. Quantum theory tells us that a radioactive atom is unstable. It will eventually decay, spitting out an alpha particle. If you leave that single atom sitting there for 1 hour, quantum equations give you an exact probability, a 50% chance that it will decay, and a 50% chance that it will remain intact. Now, ask the most fundamental question in science at 30 minutes into the hour. Can any equation in physics tell us precisely when that specific atom will decay? Classical physics answers, yes, if we just look closer at its internal components. Standard quantum physics answers, no, not even in principle. When a radioactive atom decays, standard quantum theory, developed largely by Niels Bohr, suggests that the outcome is not hidden behind variables we haven't discovered yet. The decay is fundamentally probabilistic. Before the measurement occurs, the particle's quantum wave function contains both possibilities at once. It exists in a state known as superposition. Only when the particle detector interacts with the atom does this wave of possibilities resolve into a single, concrete outcome. For the first time in human history, physics encountered an event that seemed to lack a classical cause. The domino chain appeared to break. This revelation sparked one of the greatest scientific clashes in history, a battle of minds between Niels Bohr and Albert Einstein. Einstein refused to accept that nature was fundamentally probabilistic. He revolted against the Copenhagen interpretation, famously declaring in a letter to Bohr, "God does not play dice with the universe." Einstein insisted that quantum mechanics was simply an incomplete theory, that there must be hidden variables, underlying physical rules operating beneath the subatomic surface, guiding the particle in a deterministic path that we simply couldn't see. Niels Bohr replied with equal conviction, "Einstein, stop telling God what to do." In the 1960s, physicist John Bell formulated a mathematical theorem to settle this dispute once and for all. When researchers carried out experimental tests of Bell's theorem firing pairs of entangled photons in opposite directions and measuring their properties, the results delivered a crushing blow to Einstein's dream of local hidden variables. The experiments proved that the subatomic world cannot be explained by local, classical rules operating quietly beneath the surface. Either reality at the quantum scale is inherently non-local, meaning particles can instantly influence one another across vast distances, or physical outcomes do not possess definite values until they are measured. The neat, predictable chains of classical determinism were broken forever. Yet, as physicists tried to reconcile quantum mechanics with our macroscopic world, a third, mind-bending possibility emerged. One that does not eliminate determinism, but multiplies it across the cosmos. It is called the many worlds interpretation of quantum physics, proposed by physicist Hugh Everett in 1957. Everett asked a radical question: what if the quantum wave function never actually collapses? When that radioactive atom faces a 50% chance of decaying, the universe doesn't pick one outcome at random. Instead, according to many worlds, the universe splits. In one branch of reality, the atom decays and the detector clicks. In another branch, the atom remains stable and the detector stays silent. If this interpretation is correct, the future does not exist as a single pre-written line, nor as a blank void. It exists as an endlessly branching tree of parallel timelines. Every choice, every quantum interaction, every star that could either collapse or survive, plays out in a different, real branch of an ever-expanding multiverse. In many worlds, determinism returns, not as a single track of dominoes, but as an infinite growing forest of them, where every possible line of dominoes falls along its own path. So, does the future already exist? If you lean toward classical relativity, you see a universe whose past, present, and future are bound together into a single, static, four-dimensional block. If you follow standard quantum mechanics, you see a world built on fundamental probabilities, where the future is actively being created moment by moment. And if you follow the many worlds interpretation, you see an infinite multiverse where every future that can exist does exist somewhere in the cosmic canopy. We do not yet have the final equation to declare a victor among these giant frameworks. Now, look back at that infinite line of black dominoes stretching across the wooden floor. Perhaps the final domino was already tipped long ago, locked in a timeless block of space. Perhaps the line breaks at the quantum scale, waiting for the universe to decide if the next piece falls. Or perhaps there were never 1 million dominoes in a single line, but an endless forest of them, each falling down a different path through every reality allowed by physical law. The floor remains quiet. The wave of falling wood moves forward, and the dark room ahead remains an open, breathtaking frontier. In our next chapter, we will push this quantum weirdness to its absolute extreme, exploring an experiment where choices made in the present seem to reach back and actively rewrite the history of the past. Quantum mechanics changes everything. Imagine standing on a cold, desolate beach at midnight under a moonless sky. In your hand, you hold a smooth, rounded pebble. You draw back your arm and toss it gently into the dark ocean before you. It hits the water with a soft, hollow splash. A series of clean, concentric ripples spread outward across the surface of the sea, widening silently into the gloom. You step back onto the dry sand, knowing two simple truths about the world you inhabit. First, the pebble entered the water at one precise, unmistakable location. Second, the ripples spreading across the water are waves. Continuous, smooth motions that fill space and wrap around obstacles. A pebble is a localized particle of matter. A wave is an extended pattern of motion. In our everyday world, an object is either a particle or a wave. It is not both. Now, imagine stepping onto that same beach, but instead of tossing a pebble into an ocean of water, you direct a single subatomic particle, an electron or a photon, toward a detector. When you look for the splash, there is none. Where you expect a simple, single path, you find a spread of overlapping mathematical possibilities. And if you interact with that particle to track its exact journey, the wave-like spread disappears, registering as a single, localized point. Welcome to the central, enduring mystery of modern physics, the measurement problem. To understand how quantum mechanics challenges our ordinary understanding of physical reality, we must look at the single most iconic experiment in the history of science. The double-slit experiment. Imagine a barrier with two thin vertical slits cut into its center. Behind the barrier sits a detection screen. If you fire small classical objects, like tiny steel marbles, at the barrier, some will bounce off, while others will pass through the two slits, striking the screen behind. Over time, those marbles will form two clean, vertical bands on the screen directly behind the openings. Now, shrink the experiment down to the quantum scale. Instead of steel marbles, we fire individual particles of light photons, one by one, toward those exact same two slits. Because we fire them one at a time, we might expect each photon to pass through either the left slit or the right slit, gradually building up two vertical lines on the detector screen. Instead, something remarkable occurs. As thousands of individual photons pass through the barrier one by one, they do not form two simple lines. They build up a pattern of alternating bright and dark bands across the screen. An interference pattern. This is the signature pattern created when two waves overlap, their crests and troughs reinforcing each other in some places and cancelling each other out in others. Even though the photons are released one at a time, each photon evolves as a quantum state that explores the trajectories of both slits, producing a pattern that matches wave interference. At the subatomic scale, matter and light do not travel exclusively as tiny, localized billiard balls. They exhibit wave-like behaviors that challenge our macroscopic intuition. When physicists first observed this interference, they asked a question that seems completely natural to the human mind. What happens if we place an instrument at the slits to determine which path the photon actually takes? Researchers devised delicate detectors capable of registering a photon's passage without destroying it. They activated the detector. They fired the photons one by one. The moment the physical system interacted with the detector, providing definitive which-way information about which slit each photon passed through, the interference pattern vanished. The photons no longer formed alternating wave bands. They registered as two simple, rigid lines on the back screen. The mere presence of a physical interaction that extracts path information changes the outcome of the experiment. In popular culture, this is often called the observer effect, leading to a widespread misconception that human consciousness itself causes quantum states to change. In physics, however, consciousness is not required. The shift occurs whenever a quantum system becomes entangled with its environment, a process known as quantum decoherence. When a subatomic particle interacts with gas molecules, heat, or measuring instruments, its fragile quantum superposition leaks out into the surroundings, destroying the delicate interference pattern. In 1978, the theoretical physicist John Archibald Wheeler proposed a mind-bending variation of this setup that tested the boundaries of time and cause, the delayed choice experiment. Imagine the same double-slit setup. A photon travels toward the barrier, its quantum state evolving across both paths. Under normal conditions, if left unmeasured, it will produce an interference pattern on the screen. Wheeler asked, what if we delay our decision? What if we wait until after the photon has passed through the barrier, but before it hits the final screen, to decide whether to measure its path? If the photon passed through the slits moments ago, its trajectory should already be established. Interacting with it at the very last microsecond should not be able to reach back and change what occurred earlier. Cause must precede effect. When experimentalists finally developed the ultra-fast switches and sub-nanosecond sensors required to perform Wheeler's experiment, the results were astonishing. Even when the measurement choice was delayed until the final microsecond, extracting path information yielded particle-like behavior. Omitting the path measurement yielded wave-like interference. To some observers, it seemed as if a choice made in the present dictated the particle's history in the past. Does this mean the present actively reaches back across time to rewrite yesterday? This is where physics and philosophy diverge into different interpretations. If you follow certain Copenhagen-style interpretations, you might argue that a quantum system does not possess a definite, objective history until a measurement brings it into focus. If you follow the many worlds interpretation, there is no backward-in-time causation at all. The universe simply branches, and the observer state becomes entangled with the particles' paths, preserving local physics without altering the past. And if you follow Bohmian mechanics, particles always possess definite positions guided by a non-local pilot wave, explaining the experiment without any time reversal whatsoever. The experiment itself is an indisputable fact of nature. How we explain it remains one of the greatest open intellectual debates in human history. Delayed choice experiments do not prove that human thoughts alter history. They prove something far deeper, that the macroscopic concepts we rely on to describe our world-like past trajectory and definite location do not apply to the subatomic world in the simple ways we once assumed. As the night deepens around you, look out into the quiet expanse of space. When you gaze up at the starlight touching your eyes tonight, remember that those photons traveled across thousands of light years of interstellar vacuum. During that vast journey across space, their quantum states evolved across immense distances. When those photons finally interact with the atoms in your eye or a telescope, that long, ancient trajectory is brought to a single, concrete point of contact. Whether you view that moment as a collapse of probability, a branching of realities, or a non-local interaction, one fundamental truth remains clear. We do not inhabit a world of simple, rigid clockwork. We live in a cosmos whose deepest subatomic foundations are subtle, interconnected, and far stranger than our everyday senses were built to comprehend. In our next chapter, we will return to the macroscopic realm to examine the ultimate barrier between yesterday and tomorrow, asking whether time could ever run backward and what it would look like if the entropy of the cosmos reversed its course. Can time flow backwards? Imagine holding a mug of warm tea in your hands on a cold evening. You accidentally nudge it with your elbow. The porcelain mug falls off the edge of the table, accelerating toward the floor. It strikes the hard wood below with a sharp crack, shattering into a dozen sharp ceramic fragments, while the warm tea splashes across the floor. You stand there looking down at the mess. Now, close your eyes and picture what it would look like if time suddenly turned around and ran backward. The scattered pool of tea would begin to contract, creeping inward across the wooden floorboards. The warm liquid would leap upward into the air, gathering itself into a clean cylinder. Simultaneously, the sharp ceramic shards would fly off the ground, reassembling their jagged edges mid-air, wrapping neatly around the rising tea, and landing gently back on the table, completely intact, without a single crack. It feels absurd. It feels like an obvious violation of reality. We laugh when we see a video played in reverse because our brains instantly recognize that the universe does not work this way. Yet here is the question that haunts theoretical physics. Why is this simple act impossible? If you examine the fundamental equations that govern the subatomic particles inside that tea mug, the electromagnetic forces holding the atoms together, the gravitational pull drawing the mug downward, and the kinetic collisions between the molecules, you discover something astounding. Not a single microscopic law of physics forbids the teacup from unshattering. So why does time only flow forward? And could there be places or conditions in our cosmos where time actually runs in reverse? To answer this, physicists look at the symmetries of the universe. In physics, if a law of nature works the exact same way when you flip a specific coordinate, we say that symmetry is conserved. There are three fundamental symmetries that govern our world. First, charge conjugation, or C-symmetry, which means swapping every particle with its antimatter counterpart. If you replace every electron in an experiment with a positively charged positron, the laws of physics remain unchanged. Second, parity or p-symmetry, which means looking at a physical process in a mirror, flipping left and right. And third, time reversal, or t-symmetry, which means replacing the variable for time, tollers, with negative tollers, playing the movie of the physical interaction backward. For decades, physicists believed that every individual symmetry was absolute. But in the mid-20th century, delicate particle accelerator experiments revealed a series of shockwaves. First, physicists discovered that the weak nuclear force, the force responsible for radioactive decay, violates parity symmetry. Nature, at a subatomic level, actually knows the difference between left and right. Later, experiments confirmed that certain exotic subatomic particles, called neutral kaons and B mesons, violate the combination of charge and parity, a phenomenon known as CP violation. And because a fundamental principle of physics known as the CPT theorem proves that the combined combination of charge, parity, and time reversal must always be preserved, there was an inescapable mathematical consequence. If CP symmetry is violated, then T symmetry must also be violated. At a microscopic, fundamental level, the laws of physics do possess a tiny, intrinsic preference for the forward direction of time. Subatomic interactions are not entirely symmetric when played in reverse. Nature does, in fact, carry a subtle, built-in arrow of time at the smallest scales imaginable. Yet, this tiny subatomic preference is far too weak to explain why tea mugs shatter and never reassemble. When the teacup strikes the floor, the kinetic energy of its fall is converted into acoustic waves in the air, thermal vibrations in the wooden floor, and microscopic heat scattered across billions of surrounding atoms. To make the teacup reassemble, every single one of those scattered thermal vibrations in the floorboards and air molecules would have to coordinate their movements simultaneously, striking the ceramic fragments at the exact same microsecond with the exact same vector, pushing them upward. It does not violate the laws of motion. It is simply so overwhelmingly, statistically improbable that in a universe 14 billion years old, it will practically never happen. The forward flow of time is an emergent property of statistical probability. Time runs forward in our world because our universe began in an extraordinarily low entropy, highly ordered state during the Big Bang. We are riding the statistical avalanche of that initial order spreading out into disorder. This realization leads cosmologists to ask a mind-bending question: what would happen if the expansion of our universe were to stop, reverse, and begin collapsing back down into a big crunch? If the universe began contracting, would entropy reverse its course? Would heat flow back into cold objects? Would shattered glass reassemble? Would living organisms age backward, unspilling memories from their brains until they returned to the womb? In the mid-20th century, some theoretical physicists, including a young Stephen Hawking, briefly pondered whether a collapsing universe might cause the thermodynamic arrow of time to flip backward. However, modern cosmological calculations have shown that this is almost certainly not what happens. Even if the expansion of space were to reverse and drag galaxies back together, entropy would continue to increase. Black holes would continue to merge, radiation would continue to scatter, and disorder would continue to grow. A collapsing universe would not run time backward. It would simply be a universe growing hotter, denser, and more chaotic, while time continues its relentless march into higher entropy. Yet, physics leaves open one exotic, mind-bending domain where time running backward might not be fiction, but antimatter reality. In 1948, the legendary physicist Richard Feynman introduced a radical mathematical interpretation of quantum electrodynamics. Feynman demonstrated that, mathematically, a positron, the antimatter twin of an electron, can be treated as an ordinary electron moving backward through time. When an electron and a positron collide and annihilate into a flash of pure energy, Feynman's equations can be drawn as a single electron traveling forward in time, emitting a photon, turning around, and traveling backward through time into the past. Whether antimatter literally travels backward through time, or whether this is simply a brilliant mathematical equivalence, remains an open debate among theoretical physicists. What it reveals, once again, is that time is far more flexible, subtle, and mysterious than our everyday human intuition suggests. The fact that you cannot unshatter a teacup, that you cannot undo a mistake, and that you cannot walk back into yesterday is not a flaw in human existence. It is the grand, majestic signature of our universe's origin. Every forward moment you experience, every breath you take, and every second that ticks by is powered by the lingering light of a pristine cosmic dawn. A universe unfolding its story, step by step, across the vast canvas of space. You cannot run the movie backward, and you do not need to. You are a conscious observer carried along by the most magnificent one-way journey in existence, the universe transforming its ancient order into the infinite patterns of tomorrow. In our next chapter, we will travel back to the absolute beginning of this journey, crossing 14 billion years of cosmic history to ask what happened before the Big Bang and whether time itself had a beginning. Before the Big Bang Imagine, walking due north across the icy expanse of the Arctic Ocean. The wind howls past your face. Beneath your boots, the sea ice stretches toward the horizon. Step by step, you follow your compass needle as it points steadfastly ahead. Eventually, you reach a single, mathematically precise coordinate on the globe, the North Pole. You stop. You take one more step forward in the exact same direction you were walking, and suddenly, your compass needle spins in a circle. If someone asks you to take 3 more steps north, you cannot do it. Not because a physical wall is blocking your path, and not because you ran out of energy. You cannot walk north of the North Pole because the coordinate system itself has reached its geographic convergence. Beyond that point, every direction you step is south. The question, what lies north of the North Pole, is not a mystery waiting to be solved. It is a phrase that carries no meaning. Now, turn your mind away from the Earth and look back 14 billion years into the history of our cosmos. When we ask, what happened before the Big Bang? We are assuming that time is an endless highway stretching backward into an infinite past, and that the Big Bang was simply an explosion occurring at some point along the road. What if the Big Bang was not an event in time, but the North Pole of time? To understand why physics questions the very word before, we must trace our universe back to its extreme origin. Today, space is expanding. Galaxies are drifting apart like embers scattered by a fire. If we run the tape in reverse, those embers draw closer together. Rewind 4 billion years, and our solar system dissolves into a spinning disk of gas and dust. Rewind 13 billion years, and the first stars vanish into a hot, uniform sea of hydrogen and helium. Rewind to the first microsecond after the origin, and the entire observable universe. Every star, planet, galaxy, and black hole is compressed into a region smaller than a single subatomic particle. If we apply Albert Einstein's general relativity strictly to this moment, the math leads to a state of infinite density, infinite temperature, and infinite curvature. A gravitational singularity. For decades, popular science described the singularity as the moment time began. A sharp, 0-point timestamp labeled $2. In modern physics, a singularity is not a physical place or a magical event. It is a signpost indicating that general relativity has reached the limits of its validity. At the microscopic scale of the early universe, a period known as the Planck epoch, the gravitational field was so concentrated that quantum effects could no longer be ignored. Smooth general relativity broke down, requiring a theory of quantum gravity that science is still striving to complete. In 1983, theoretical physicists Stephen Hawking and James Hartle proposed a mathematical framework designed to bypass this singularity entirely, the no-boundary proposal. Hawking and Hartle asked a radical question: what happens if time, at quantum scales, does not stop at a sharp point, but changes its nature? In classical physics, space has 3 dimensions, and time has 1. Time moves in a single, unyielding direction, from past to future. Under the no-boundary proposal, as you trace history backward into the Planck epoch, intense quantum fluctuations cause the dimension of time to behave mathematically like a 4th dimension of space, a concept known as imaginary time. Think back to the North Pole. As you approach the pole, the lines of longitude draw closer together, smoothly converging at a single, rounded point. There is no sharp corner. There is no edge where the Earth drops into nothingness. Hawking argued that space-time at the origin of the cosmos was shaped in the exact same way. As you travel back toward the Big Bang, time smoothly rounds off into space. The universe had no sharp creation moment, no first tick of a clock, and no singular boundary where non-existence suddenly became existence. Under this hypothesis, the universe is entirely self-contained. Asking what happened before the Big Bang is like asking what lies north of the North Pole. The word before simply dissolves. Is the no-boundary proposal the final answer? Physicists remain cautiously skeptical because we cannot yet test the Planck epoch directly. Other theoretical models propose alternative ways of visualizing the origin. In the framework of eternal inflation, pioneered by physicists like Alan Guth and Andrei Linde, our observable universe is merely one isolated bubble that settled out of a vast, continuously inflating false vacuum. In this model, what we call the Big Bang was simply the local end of inflation in our corner of space, while the surrounding cosmos continues to inflate, spawning other universes endlessly. In other models, such as those derived from loop quantum cosmology, quantum forces at extreme densities create a repulsive effect, suggesting the Big Bang was actually a big bounce. A transition from a contracting previous state into an expanding one. Yet every one of these advanced theories points toward a single, humbling realization. Our intuitive human concept of time, a linear stream flowing smoothly from a clear before to an obvious after, is a local feature of the macroscopic world we inhabit. It is a framework built for our daily lives on Earth, not an absolute property of the cosmos at its origin. When we push our questions back to the birth of space and time, the language of everyday human experience reaches its limit. We want a story with a beginning, a middle, and an end. We want a cause that precedes an effect. We want to stand outside the universe, look at a clock, and ask what was happening 5 minutes before the curtain rose. Nature owes no obligation to match our daily intuition. The origin of our cosmos may not be a mystery waiting for a timestamp. It may be a profound geometric boundary, a place where space and time merge into a quiet, self-contained architecture. In our next chapter, we will turn our gaze from the primeval origin to the far distant horizon, projecting our equations trillions of years into the future to discover what physics predicts for the ultimate fate of space, matter, and time itself, the end of time. Imagine holding an incandescent glass sphere in the palm of your hand in a vast, dark room. The sphere glows with intense, white-hot heat, casting bright light against the surrounding shadows. You set it down on a heavy iron table and watch it. At first, nothing seems to change, but slowly, imperceptibly, the white light shifts to a warm amber. The amber deepens to a dull, crimson ember. The heat radiates out into the cool air of the room, spreading thin, dispersing until the sphere turns dark, smooth, and cold to the touch. If you leave that glass sphere sitting on the iron table for 1,000 years or 1,000,000,000 years, it will never gather that scattered heat back out of the room, reignite its core, and shine again on its own. Now, look up at the night sky. Every star blazing in the void, from the blazing blue supergiants to the quiet red dwarfs, is a glass sphere sitting on the cold table of the cosmos. They are burning through finite reserves of nuclear fuel. They are radiating their heat out into the vast, expanding emptiness of space. And the universe, according to the fundamental laws of thermodynamics, is slowly, silently running down its battery. We spend much of our lives asking where the universe came from, searching for the first tick of the cosmic clock. But modern physics allows us to look in the opposite direction, projecting our equations forward across unfathomable spans of time to answer an even quieter, darker question: how does time itself end? To trace the ultimate fate of time, we must travel forward across timescales that dwarf all of human history. 100 billion years from now, the night sky will look fundamentally different, because the expansion of space is accelerating, driven by the mysterious, repulsive influence of dark energy. Distant galaxies are being pushed away from us faster than the speed of light. One by one, the island universes that currently dot our telescopes will slide beyond our cosmic horizon. The sky outside our local galactic cluster will turn completely, utterly black. Trillions of years into the future, the era of starlight draws to its natural close. One by one, the great star-forming gas clouds in galaxies will run out of hydrogen. The massive blue stars will explode as supernovas, leaving behind neutron stars or black holes. The long-lived red dwarf stars that can burn quietly for trillions of years will slowly exhaust their nuclear fuel, dimming into cold, dark spheres of helium and carbon known as black dwarfs. The last star in the universe will blink out. The cosmos will enter the degenerate era. Galaxies will consist entirely of dead stellar remnants, floating silently through an ever-expanding, freezing void. Yet even in this dark, frozen cosmos, time has not reached its end. If we wait 10,434 years, a number represented by a 1 followed by 34 zeros. Current theoretical physics suggests that even the fundamental building blocks of matter may begin to dissolve. If protons are unstable, as many grand unified theories predict, the solid dead stars floating in the dark will slowly decay. Atom by atom, the stellar corpses will evaporate into a faint drizzle of leptons and photons. By 10 nullas and 40 nullas years, the universe enters the black hole era. The only complex structures remaining in the cosmos will be supermassive black holes sitting in the center of dead, empty galaxies. For unfathomable eons, these black monsters will rule the dark. But as Stephen Hawking proved, even black holes are not immortal. Through the slow, relentless process of Hawking radiation, black holes slowly leak energy back into space. A black hole with the mass of a galaxy will quietly evaporate over 10 lalas, 100,000 Tottadan lalas years, a duration known as a Gugol years. When the last supermassive black hole completes its final faint flash of evaporation, the universe will enter its final, ultimate phase, the era of dark energy, or the Big Freeze. In this distant, empty epoch, the universe reaches a state of maximum entropy. a condition known as thermodynamic equilibrium, or the heat death of the cosmos. The temperature of space drops to a fraction of a degree above absolute zero. There are no stars, no planets, no black holes, no chemical reactions, no sources of usable energy. There is only a sea of extremely long wavelength photons and dark energy, diluted across an unimaginable expanse of empty space. And here, we confront a mind-bending physical realization about the nature of time itself. When a system reaches maximum entropy, when no temperature differences remain, and when no physical transformation can ever occur again, the concept of time loses its meaning. Recall what we discovered in our opening chapters. Clocks do not measure a physical substance called time. They measure change. In a universe where nothing moves, nothing transforms, nothing interacts, and nothing decays, there is no before and no after. The arrow of time, driven for trillions of eons by the spreading of entropy, finally flattens out into an eternal, featureless baseline. Time does not end with a dramatic cinematic crash. It dissolves because there is nothing left to record its passage. Are there alternative endings predicted by the equations of cosmology? Depending on the true nature of dark energy and quantum fields, physics offers three other potential finales. If dark energy strengthens over time, an equation of state known as phantom energy, the acceleration of space could become violent enough to trigger a big rip. 60 million years before the end, galaxies are torn apart. 3 months before, planets are ripped from their orbits. In the final fraction of a second, atoms themselves are torn asunder by the expanding fabric of space. If dark energy is negative, the expansion could reverse into a big crunch, collapsing all matter back into an ultra-dense state. Or, if our universe sits in a temporary, metastable energy state known as a false vacuum, a random quantum fluctuation could trigger vacuum decay. A bubble of true vacuum would expand outward at the speed of light, instantly rewriting the laws of physics and erasing all matter in its path without warning. Whether through the quiet decay of the Big Freeze, the violent tear of the Big Rip, or the sudden sweep of vacuum decay, every model in physics points toward a universe that is dynamic, finite in its structural lifetime, and bound by natural law. As you lie in the quiet dark of your room, let the immense scale of this cosmic timeline rest gently in your mind. We inhabit an extraordinary, fleeting window in the history of the universe, the era of starlight. We live in the brief, brilliant epoch where stars shine, planets orbit, rivers flow, and conscious minds can look up at the dark sky and understand the laws that govern the cosmos. The ultimate end of stars and time does not diminish the value of this moment. It illuminates it. Our existence is a rare, exquisite flame burning brightly in a vast cosmic night. A fleeting, beautiful opportunity to observe, to learn, and to experience the grand story of reality. In our next chapter, we will bring all these threads together, tracing the evolution of time from Newton to Einstein, through quantum mechanics to cosmology, to ask the ultimate question: is time a fundamental structure of reality, or an illusion woven by the human mind? Is time just an illusion? Imagine standing in a silent art gallery late at night. On the far wall hangs a vast oil painting. It depicts a stormy ocean at sunset. Giant, emerald waves frozen mid-crash, white foam suspended like glass needles in the air, and a wooden ship leaning precariously against the surge. You step closer to the canvas until your eyes are only inches from the surface. Up close, the stormy ocean disappears. The raging waves, the dramatic light, and the sense of violent motion dissolve into a static collection of dry, flat oil pigments resting on woven canvas. There is no motion here. There is no water. There is no wind. The storm, and the sense of passing time exist entirely in the way your brain organizes those microscopic dabs of paint into a story. Now, step back from the painting and look at the physical universe itself. For 12 chapters, we have tracked time across every frontier of science. We watched humans build clocks from shadows and atoms. We saw Einstein warp time with speed and gravity. We descended into black holes where space and time swap places, and we ventured into the subatomic realm where cause and effect lose their rigid order. Now we must confront the central question that sits at the convergence of modern physics when we look at the universe at its most fundamental level. Is time a fundamental pillar of reality? Or is it, like the storm in that painting, a feature that emerges only when we view the macroscopic whole? To understand why modern physics questions the fundamental nature of time, we must look at a deep, century-old conflict between our two greatest scientific frameworks. In general relativity, Albert Einstein showed that time is not a rigid, universal background. Time is dynamic, flexible, and bound to space, warping around speed and mass to form four-dimensional spacetime. Yet in Einstein's equations, spacetime remains a continuous, real physical structure. In quantum mechanics, however, time plays a completely different role. It is treated as an external, background parameter, an unchanging clock ticking outside the subatomic system. When theoretical physicists attempt to merge these two frameworks into a single unified theory of quantum gravity, a deep mathematical clash occurs. In certain approaches to canonical quantum gravity, such as those utilizing the Wheeler-DeWitt equation, for some theoretical physicists, this implies that at the deepest quantum level, the universe may be fundamentally timeless, that the clock is not an intrinsic property of subatomic nature. Yet, this remains an interpretation. Other physicists argue vigorously that the disappearance of time is merely an artifact of how the equations are set up, or that time is hidden within internal relationships between quantum states. Physics does not present a single verdict. It presents a profound debate. If fundamental reality does not contain an intrinsic clock, how does our everyday world produce seconds, hours, and aging? One prominent proposal explored by theoretical physicists is the concept of emergent time. Consider a single molecule of water floating in space. That single molecule does not have a temperature. It is neither hot nor cold. It does not have fluidity. It cannot be wet. They are emergent properties, phenomena that only appear when trillions of water molecules interact together as a collective system. In frameworks like loop quantum gravity and certain approaches to string theory, some researchers hypothesize that time works in a similar way. At the smallest microscopic scale, the Planck scale, fundamental reality may consist of quantum networks, geometric nodes, or information loops that contain no built-in temporal dimension. Time, in these models, is an emergent phenomenon. It arises when you step back from microscopic subatomic nodes and observe vast, macroscopic collections of matter and energy interacting through statistics and entropy. Just as a single molecule has no temperature, a single quantum node may have no time. Yet, this remains a hypothesis under active investigation, not a settled law of nature. Another influential approach is the thermal time hypothesis, formulated by theoretical physicist Carlo Rovelli and mathematician Alain Connes. Rovelli proposes that time may be intimately connected to information and thermodynamics. Because a human observer cannot track the precise quantum state of every single atom in the universe, we perceive reality through coarse-grained statistical averages. When we observe these statistical averages, entropy increases, heat flows, and the sensation of time passing naturally arises from our partial, incomplete perspective. In this framework, the flow of time is a relational effect, a consequence of how a macroscopic system interacts with its environment and our limited access to complete microscopic information. Yet, like emergent time, the thermal time hypothesis is an elegant proposal, not a universal consensus. Other physicists hold fast to the view that time is fundamentally real, that absolute temporal structures or relational time flows are necessary to make sense of an expanding, evolving universe. Step back once more from the canvas in the art gallery. Look at the dabs of paint that form the raging ocean. If you look closely enough, the storm vanishes into static pigment. Yet step away, and the storm comes alive. The history of our understanding of time is not a straight ladder ending in a single, final answer. It is a sequence of breathtaking conceptual shifts, from Newton's absolute clock to Einstein's flexible spacetime, to quantum mechanics' external parameters, to contemporary proposals of emergent and relational time. Whether time is a fundamental building block of the universe or an emergent feature of complex systems remains one of the greatest, most open questions in modern science. Physics has taken us remarkably far. It has shown us that Newton's absolute clock is gone, that Einstein reshaped time into geometry, and that some approaches to quantum gravity suggest time itself may emerge from something deeper. Whether time is truly fundamental or emergent remains waiting for the next revolution in human thought. Step back once more from the canvas. The static strokes of paint haven't moved. Yet in our journey through them, we found a universe in motion. In our final chapter, we will step beyond the equations and metrics of science to take a slow, contemplative journey beyond time itself, reflecting on what it means to be a conscious human being living within a brief, beautiful spark of the cosmos. Beyond time, imagine an immense, dark theater. The auditorium is silent. The house lights are low, casting long, still shadows across hundreds of empty velvet seats. High above, a single spotlight strikes the center of the stage, cutting a narrow cone of clear light through the black air. Inside that circle of light, a dancer takes a single step. For a brief moment, her movement fills the space. She turns, leaps, and reaches toward the darkness beyond the edge of the beam. To her, that brightly lit circle holds everything: her previous steps, her current movement, and the trajectory of her next turn. Then, she steps across the perimeter. The beam catches only empty air. The stage returns to silent dark. Now ask the central question that has brought us to the end of our journey. What was the spotlight? Was the spotlight time itself? A physical beam sweeping across a static stage? Was it consciousness? A temporary flare of awareness illuminating an indifferent universe? Or was it something far stranger? The realization that without the dancer inside the beam, the concept of a stage has no meaning at all. Throughout this documentary, we have pursued a single, fundamental mystery. What is time? We began with the simple clocks of human history, shadows on stone, swinging pendulums, and vibrating quartz crystals. We thought we were measuring a cosmic river flowing smoothly outside of us. Then physics forced us to abandon that simple comfort. Albert Einstein proved that time is not a universal river, but a flexible dimension woven into space, stretching, slowing, and warping around mass and motion. Black holes showed us places where the geometry of reality fractures, where space and time literally trade places. Quantum mechanics revealed a subatomic realm where cause and effect lose their macroscopic order, where measurements reshape outcomes, and where the past itself resists simple definition. And cosmology took us to the edges of reality, from the primeval boundary of the Big Bang, where time may have rounded off into space like the North Pole, to the far future of the Big Freeze, where entropy flattens and time dissolves into stillness. Yet, as we stand at the edge of modern knowledge, we face a profound, lingering paradox. Every equation we have written, every atomic clock we have calibrated, and every theory we have constructed has brought us back to the same fundamental realization. Time is not merely something we observe in the universe. Time is the very lens through which a finite mind perceives an infinite cosmos. Consider what happens when science attempts to remove the observer from the universe entirely, in a purely objective, mathematical view of the cosmos, whether visualized through the static four-dimensional geometry of relativity or the timeless wave functions of canonical quantum gravity. There is no glowing arrow labeled now. There is no physical marker distinguishing 1926 from 2026 or 3026. Equations do not experience a memory fading into the past, nor do they feel the anticipation of an unwritten future. The past does not feel gone. To an equation, the future does not feel unknown. The flow of time. The sensation of moments marching forward in a single, unyielding line requires an observer capable of storing memories, processing entropy, and anticipating outcomes. This does not mean time is an illusion without consequence, nor does it mean the universe requires human minds to exist. It means that what we call the passage of time is an active, ongoing relationship between physical law and conscious perception. We are not passive spectators standing on a riverbank watching reality float past. We are the point where physical law becomes aware of its own geometry. Step back once more to the spotlight in the theater. Define the beam now. The dark stage is the timeless, vast ocean of physical laws. The quantum networks, the gravitational fields, and the cosmic coordinates that simply are. The spotlight is consciousness. A brief, fragile thermodynamic event powered by the heat of stars burning through low entropy in a temporary corner of space. And the dance inside the beam is our brief, magnificent opportunity to measure, to question, and to understand. We do not have a final theory of everything. Quantum gravity remains incomplete. We do not know with absolute certainty whether time is fundamentally woven into the fabric of nature or whether it emerges from deeper quantum information. And that uncertainty is not a flaw in our science. It is the very engine of human progress. If the universe were simple enough for us to fully comprehend in a single century, we would be too simple to comprehend it at all. The mystery remains open. The frontier remains vast. We inhabit a rare, luminous window in cosmic history, the era of starlight. We live in an epoch where the universe is cool enough for complex matter to form, warm enough for liquid water to flow, and young enough for stars to light the night sky. We do not need to fear the passage of hours, nor do we need to demand that physics grant us an easy, permanent reassurance. The beauty of our existence does not come from lasting forever. It comes from the fact that within a universe of cold matter and physical laws, a brief spark of awareness flared up, looked out into the dark, and built instruments to measure the age of the stars. Time gave us the space to ask where we came from. Science gave us the language to seek the answer. And perhaps that is the greatest gift time has ever given us. Not simply the ability to measure the universe, but the opportunity for the universe to become aware of itself, if only for a little while. The spotlight remains lit, the dark stage waits, and the quest to understand continues.